Hello to all of you and welcome back to my SB2 channel. This lecture is all about the enthalpy. We're going to look at the introduction. We're going to be looking at the pressure, volume, work, as well as the enthalpy change. Specifically, we're looking at the enthalpies of reactions, and I also have a practice for you just like always. Okay, so starting by introduction, as you guys know, there are so many chemical and physical changes that are happening around us. These are just a few common examples. We have photosynthesis in plants. We have evaporation of water from the lake. We have a reaction that we are doing in the lab, right, in our beaker. And all of these reactions are going to happen at constant pressure of the earth, which is the atmospheric pressure, right? Now, this process may involve in the releasing or absorbing of the heat and can also be accompanied by work done by or on the system, right? As we talk about them in our previous lecture. Now, to analyze these changes, it is always very helpful to have a thermodynamic function that is actually primarily relating to the heat flow, right? Whether we are, gaining heat or losing heat under the conditions of the constant pressure. This is the key. The constant pressure, a key thermodynamic quantity called enthalpy, one more time, enthalpy, that is serving for this purpose. So the enthalpy, which is H, is defined as the internal energy plus the product of the pressure volume of the system. It goes by the H, which is our enthalpy, and that is equal to your E, your internal energy, plus pressure volume product. I'll talk about this pressure volume product in a little bit more details on the next page, but for now, keep that in mind. Both P and V are your state functions, just like your E, your internal energy. That means they are going to be dependent only on the current state of the system, right? And not the path that we are taking to reach to the products, right? So since energy, pressure, and volume are all state functions, therefore the enthalpy is also going to be an state function, okay? Now let's talk about this PV in a lot more details on the next page. Okay, so the pressure volume work, okay, it's a work. So I have to go by W. This happens when a gas expands or maybe compressed, causing a change in the volume, and that has to be done under constant pressure. So mathematically, remember work was W, and that goes by negative P times by the change in your volume. That's your delta V. Okay, so what I have here is my P, which is my pressure. That is going to be always the external pressure. We have delta V, the change in the volume. And a quick reminder, delta is final minus initial, right? Final volume minus initial volume. And I also need to have this negative sign because if the gas expands, then you would have a positive change in your volume. Then the system is going to lose energy, right? So that means it does work on the surrounding, and that's why I need to have this negative sign, okay? If you're having trouble understanding this positive negative sign for W, please look back to the previous lecture. I talked about all of that in my previous lecture, okay? Okay, now we're going to return to our discussion of enthalpy. So when a change happens at constant pressure, the change in the enthalpy can be given by the following. So I have my delta H that goes by delta E plus PV. And I'm trying to keep this PV for you in red so that will be easier for you to follow the discussion, okay? Now, because my pressure is constant, the delta has nothing to do with the pressure, right? So it will be P times by delta V. So this means that the change in the enthalpy equals the change in your internal energy, right, your delta E, plus the product of the constant pressure and the change in the volume. Now, a quick reminder, we said that delta E goes by Q plus W, and I'm just going to replace the term that we have in our previous slide for my W. That means your delta E goes by Q minus P times by delta V. And now what I'm going to do here, bear with me. I'm going to replace this whole thing here for my delta E. Okay, now guess what? You have negative P delta V plus P delta V. So they can actually cancel each other out. So all I have at the end is just my heat. So I can say the change in the enthalpy equals the heat gained or lost at constant pressure. Okay, that's a very good point to always keep that in mind when you are looking at the change in the enthalpy of our reactions. Okay, perfect. Look at the next slide. Okay, now we're going to be specifically looking at the enthalpies of reactions, right? Our chemical and physical reactions. So here it says the enthalpy change that accompanies a reaction is called either the enthalpy of reaction, or you can say the heat of reaction, right? And we typically go by the delta H Rxn, and this Rxn is just the abbreviation for your reaction. And because I have delta, I can say final minus initial, right? So the enthalpy of reaction is given by the delta H of final, which is going to be, guess what? Your product, right? Minus your initial, which is going to be your reactants. So we're looking at the H of the product, the H of the reactants, and then we take the difference of these two. Okay, cool, cool. Okay, now that we know what is the enthalpies of reaction, I'm going to have a little bit more details about more like a properties or maybe a guideline, right? So that we can kind of understand the, thermo chemical equations or even the enthalpy diagrams better. Okay, so the first thing is the enthalpy is an extensive property. So what does that mean? It means that if I give you a reaction and you also have the delta H for that, right? If you double that reaction, you need to double your delta H. You always need to scale your delta H with respect to your reaction. The second one is the enthalpy change for a reaction is equal in magnitude, but it must be opposite in the sign to the delta H for the reverse reaction. So that means reactions are going to have, let's say, positive delta H in one way. If you flip the reaction, if you have the reverse reaction, we expect to get a negative delta H for that, right? The last one is the enthalpy change for a reaction is also going to be depending on the state of your reactants and products. So we have to be careful with, solid, liquid, or maybe gas for our reactants and product. If you change that, we're going to have different delta H for our reactions. Okay, excellent. So now we're going to look at this practice. It says we have this reaction, which you know what is this reaction, right? This is a combustion reaction. And as you can see, we have delta H as negative 890 kJ. The question is how much heat is released when we have 4.5 grams of methane at constant pressure system. Okay, so the first step is you've got the mass and you have to convert that to the moles. That means you need to calculate your molar mass using your periodic table, right? That would be about 16 grams per mole. When you get the moles of methane, you have to adjust that to calculate your delta H, right? Depending on your reaction. Okay, so let's do the first step. You've got 4.5 grams of methane. Considering your molar mass, every 16 grams is going to give us 1 mole, right? And then you can cancel out the grams of methane, by the way, you know how to do that. What we have at this moment is the moles of methane. Now, according to this reaction, if I burn 1 mole methane, I'm going to release 890 kJ or kilojoule of the energy, right? So you have to consider that as well. And we're going to have 250 kJ at the end. Okay, cool, cool. Thank you very much for bearing with me. If you enjoyed this video, make sure that you give it a thumbs up, and you can also share that with your friends. If you're enjoying the content and you want to keep learning with me, you can hit that subscribe button. You can turn on your notification bell so you're not going to miss out any of our future videos. I would love to hear from you guys. You know that, right? So let me know. You can drop a comment below or you can email me. If you guys have any questions or any topics, right, that you would like me to cover that for you. Your support means the whole world to me. Thank you so much. Take care of yourself, and I'll see you on the next one. Bye bye for now.